All right, buckle up your brain, mass stoichiometry. Now I should probably tell you that a lot of students find mass stoichiometry or stoichiometry in general to be one of the more, let's call them intimidating things in this course of chemistry. And I should tell you that, but I'm not going to. What I do want to tell you is that if you understand what's going on in stoichiometry, it'll make a whole lot more sense. If all you're doing is trying to follow a pattern, it'll work not very well. Let's just be honest. Okay, let's start with making a burger. And I don't know what the 5 is doing there, but it'll come back and be important later. If you were making a hamburger, you would need to have certain ingredients, and you would end up putting those ingredients together to make a final product. If you wanted to make 5 burgers, see the 5 comes, you would need to take all those ingredients and have them scale them up. Take them all by 5. So instead of 2 buns, you'd need 5 times that. Instead of 1 patty, you need 5 times that. And the same would be true if you were making 500 or 5,000. You would have to just increase the number of ingredients. But the reality of the story is that the recipe would stay the same. To make a burger, it's the same recipe every time. And I realize those burgers don't follow that recipe, but it's the best I could do. Okay, how does that affect what we do in chemistry and what in the world is stoichiometry? Well, stoichiometry is mass relationships within a chemical reaction, because we know that a chemical reaction, A, deals with things that are really, really, really small, and we're dealing with lots of them. And we also know that we can work with masses. We can put a thing on a balance and find its mass. And it also means that we're going to take a reaction, we're going to scale it up. Because when we look at a reaction, in most cases, it's not realistic. If I asked you to read that reaction, you would probably tell me 1 molecule of nitrogen, 3 molecules of hydrogen, and so on. But that's not realistic. We're never going to have a reaction where you actually just have 1 molecule and 3 molecules of hydrogen. Now, we already know about moles. We could read that reaction with moles. 1 mole of nitrogen reacts to 3 moles of hydrogen to produce, and so on. So if we start counting the reaction in terms of moles, like we're trying to count chemical formulas in terms of moles, now things are going to start to work a little bit better. But we run into a new problem. Now let's start with counting reactions in molecules to quickly take us into moles, because molecules we understand. If I asked you to answer that question, you would probably set up a ratio like this, and you would solve for X and tell me you'd need 108 molecules, and that's perfectly correct. The problem is molecules are just not a realistic counting tool, so we need to ask the question in terms of moles. Now we already know that moles keeps the numbers the same. It's a more convenient tool, but it also is still an uncomfortable one for us and not a very familiar one for us. But what do? Well, we do the same thing because the recipe stays the same. So we set up the ratio exactly the same way. The only thing that's different is now we've got fractions of moles instead of full molecules. And we would solve it the same way, and we'd come up with 7.2 moles of hydrogen. Too easy. It's the same thing we were doing before. If we were to ask the question again, you would set it up the same. You would find a spot where the recipe is followed, or you would figure out what the recipe is. So in this case, 1 mole of nitrogen requires 3 moles of hydrogen, and you'd solve for X. Now, I do want you to try this one on your own. You pause it if you need to, but exactly the same thing. You're going to find the recipe, and you're going to answer the question. Okay, you did that? I hope you did that, because this is going to be a really, really big thing for us. But please check your answer. You'll notice I didn't set it up for you. So if you haven't pushed the buttons, if you haven't tried that, please do. It's going to be extremely important for you to do that. Okay, but we said stoichiometry is mass relationships, and we don't actually count out numbers of moles. We calculate numbers of moles. So how do we do that? So we're going to take a reaction where we're going to know a certain amount of mass, and we're going to figure out a certain amount of mass. So we've got 31.6 grams of nitrogen, and we want to know how much hydrogen that's going to require. There's going to be 3 steps. Step 1 is to convert the mass that you know into numbers of moles. We know how to do that. So the question was 31.6 grams of nitrogen. Well, how many moles is that? So we do mass divided by molar mass to calculate numbers of moles of nitrogen available. And in this case, it's 1.13. And again, push the buttons. If you haven't calculated that, then not knowing where this number comes from is going to be a huge problem. You need to know where it is. Second thing, we're going to do that step we were doing a moment ago, and we're going to calculate how many moles of hydrogen that means from that number of moles of nitrogen. So we just got finished calculating 1.13 moles of nitrogen. How many moles of hydrogen does that require? So we set up that recipe ratio to figure out how many moles of hydrogen, and we get 3.39. It's the same way we would have in the previous couple steps. Now, that 1.13 moles of nitrogen came from the previous mass, so I could have asked that question. How many moles of hydrogen come from or would react with 31.6 grams? Finally, so there's 3 steps. Here's number 3. We're going to convert those moles that we just calculated, the moles of the unknown thing, the hydrogen, convert that into mass, because that was what we were asked for in the first place. So in other words, what mass of hydrogen is 3.386 moles of hydrogen? Well, that's a question we were doing a while ago as well. Mass is number of moles times molar mass. That's easy. So we take the number of moles that we have and we multiply it by its molar mass, and we get that mass, 6.77 grams. But keep in mind that that mass came from a number of moles, which came from a different number of moles, which came from a mass. So really, we just calculated how many grams of hydrogen we need to react with 31.6 grams of nitrogen. 3 steps. And we have to do all 3 steps every single time. Okay, write this down and pause it if you need to. I'm going to roll on pretty quickly because I'm worried this is going to drag on and be really, really long. Okay, really important at the bottom. Whether you write it down or not, you have to remember it every single time, all 3 steps. Okay, so we're going to try it. We're going to do this together. These are the steps we're going to go through, and these are basically the things we're going to be picking up. Notice that the step 2 has 3 carbon dioxides over 4 waters. Those numbers, 3 and 4, come out of the balanced chemical reaction. That's the recipe. Okay, we're going to start by converting from mass that we know, which is 53.6 grams of water. We're going to convert that into number of moles, mass divided by molar mass. We're going to do the math, and we're going to come up with a number of moles. Now we're going to take that number of moles, and using the recipe, we're going to convert to moles of unknown. In this case, the moles of unknown, we're looking for carbon dioxide. So there's the reaction. That's where we get our recipe from. That's where the 3 and the 4 come from. I like putting the one that I'm looking for on top. I just find that math easier to solve, but it really doesn't matter. And we calculate, do the math to 2.235, and I know I should be looking at significant digits, but whatever your calculator says, I want it to be as close as I can to what I've got. Finally, number of moles, convert that to mass. So we need to know how many grams, what mass is that 2.235 number of moles. Mass is number of moles times molar mass. And of course it's the molar mass of carbon dioxide in this case, which we figure out, and we find out that we've got 98.34 grams of carbon dioxide. So that original mass of water also means 98.34 grams of carbon dioxide. Whew, a lot of work, I get it, but it's the same kind of thing every single time. Okay, I'm going to leave you with one. We'll pick up the answers in a moment. Please pause this so you can try it on your own. And step 1, if you have not done it yet, please do. There's your answer for step number 1. There's your answer at the end of step number 2. There's your answer for step number 3. You'll notice the units. Please make sure you have units. All those answers need to have units in them. Okay, going to leave you at this one. We're going to check it, and we'll make sure that we've got this one squared away. Here it is. Pause it, write it down, figure it out. Stoichiometry is going to be a really big part of what we do in this course, so and also later units as well, so we need to make sure that we understand the big picture of stoichiometry. What is the big picture of stoichiometry? The big picture of stoichiometry is here. Now, we always start with something measurable. Right now, I can measure mass. And we finish with something measurable. Right now, I'm finishing with mass. But it doesn't have to be mass. It could be a volume of a solution. It could be a volume and amount of gas. But we're always going to convert it into moles. We're going to shuffle around the reaction with moles because reactions work by moles. And then we'll turn it back into something we can measure. Okay? It's actually not that hard. So I kind of understand that, but don't get wrapped up in that and don't worry about it. Okay? We'll get it sorted out. Talk to you in class.